averages them together. And that's what comes up on the next slide. So here's the estimate of the common odds ratio, controlling for age. If you average those two numbers, the 2.3 with the 1.7, we get an adjusted odds ratio, free of confounding. That's equal to 2.4. So in summary, what did we have? Let me just skip ahead 2 slides. The crude odds ratio was 2.03, adjusting using a technique called Mantel-Hansel estimation. Adjusting through stratification, we get an odds ratio of 2.04. If I go back to my printout, we even get a confidence interval around that adjusted odds ratio. The confidence interval goes from 1.55 up to 2.68. This is how you control for confounding using stratification. Divide people into risk groups who have similar values of the confounder, young people in one group, old people in another group. You compare young men to young women in one analysis, old men versus old women in another analysis, and then you average the results together, and that's where this number 2.04 comes from. Well, that's how you can control for confounding with stratification. It's fairly simple. All you have to do is break people into subgroups. Fairly straightforward. All you're doing is calculating odds ratios in each of the subgroups and averaging them together. It does require categorization. You have to take a continuous confounder like age, and we have to break them up into age groups. We call young people if they're under age 55, old people if they're above age 55. So what happens is you have to group people into categories if you're going to stratify. And a problem with stratification is it's not very practical. I think I mentioned this a couple of weeks ago for controlling for many confounders simultaneously. Because here I've had to make 2 age groups, young and old, to control for age. I'm probably doing a very rough job of controlling for age because I'm saying anybody who's older than 55 is old. Well, a 56-year-old person is different from an 86-year-old person. So maybe that age range above 55 is too wide. Maybe the men in that table are in their 50s. Maybe the women in that table are in their 70s, and that's not a fair comparison. So maybe you'd have to break ages not just into young versus old, but maybe 40-year-olds, 50-year-olds will be in another group, 60-year-olds will be in another group, 70-year-olds will be in another group. Moreover, if we also want to control for blood pressure, let's suppose blood pressure was either hypertension versus no hypertension. Each of those age groups would have to be further stratified by high versus low blood pressure. It turns out that if you have 5 binary confounders, young versus old age, hypertension versus not hypertension in terms of blood pressure, physically active versus not physically active, high cholesterol versus low cholesterol, diabetes versus no diabetes. You try to stratify by all 5 of those binary confounders at once, you're going to end up with 32 subgroups, 32 strata. One of them are going to be made up of young diabetics who have low cholesterol but high hypertension, who are not physically active. You're going to compare all the men in that group to all the women, and you're going to argue that that's a fair comparison because everybody in that table had similar values with respect to age, blood pressure, cholesterol levels, physical activity, and diabetes. The problem is you only had 1,300 people to begin with, and now you're dividing those 1,300 people into 32 subgroups, getting fewer people in each of those subgroups. You're losing information because you're spreading your data. And as you make more and more subgroups, you're going to ultimately run out of data to fill into those subgroups. So stratification is not very feasible. You have multiple confounding factors. The alternative is to use a regression model. And to show you how that works is let's look at the simple example of just controlling for a single confounding factor. We have a binary outcome, whether a person did or did not develop heart disease, a binary exposure, whether you're a male or a female. Then we have a binary confounder, whether you are young versus whether you're old, with 55 as the cut point. So X1 is going to be 1 if you're a male and 0 if you're a female. X2 is going to be 1 if you're old, 0 if you're young. So the model we're going to fit is going to look like the following. I'm going to say your log odds of disease is equal to B0 plus B1 times male, just like we had before. But now we're going to add another term to this model, plus a B2 times age 55. Age 55 is 1 if you're above 55, 0 if you're below 55. What is this model doing in terms of controlling for age? If I go back to the previous slide, actually the slide before that, here's a model. It says your log odds of getting disease depends on your value for x1 and depends on your value for x2. Think of x1 as being male, 1 if you're a man, 0 if you're a woman. x2 is age, 1 if you're 55, 1 if you're above 55, 0 if you're below 55. What does this model imply about the meaning for B1 and the meaning for B2 and the meaning for B0? Well, this model implies certain statements. If you are a male, x1 equals 1, and you're young, x2 equals 0, the model says for you that, if I go back to the previous slides, that your value for your log odds of disease is B0 plus B1 times 1 plus B2 times 0. And that becomes B0 plus B1 times 1 is a B1 plus a B2 times 0 is 0. On the other hand, if you're a woman who's young, the model says your log odds of disease is equal to B0. So just like what we talked about last week, if I compare the young men to the young women, by comparing these two statements which are implied by the model, the right-hand sides differ by the B1 term. And just like we did last week, that's going to be the log odds ratio comparing young men to young women. So the model implies that B1 is the effect of being a male versus a female among young people, comparing young men to young women. But what if I was looking at old men and old women? In other words, the value for x2 was 1 for both the men and the women. If you're an old male, your log odds of disease is B0 plus B1 times 1 because you're a male, plus B2 times 1 because you're old. If you're an old woman, the model says your log odds of disease is B0 plus B1 times 0, which is 0. That goes away. But you do get the B2 terms because you still are old. It's B2 times 1. And now compare these two equations, the old men versus the old women. The right-hand sides differ by B1. So again, B1 now is meant to be the log odds ratio for comparing old men to old women. What this is implying, regardless whether you're young or if you're old, B1 is comparing similarly aged men to similarly aged women. It's like looking within the looking within the young group of people, doing an analysis just comparing men to women using just young people. Then doing another analysis using just old people, old men versus old women, getting odds ratios in both situations, and the model assumes that those odds ratios are representing the same value. What it does is it does these separate calculations and then averages them together just like stratification. So when we fit a model that contains a term for the confounding factor that we want to control for, the coefficient of our exposure term takes on a different meaning. It's now representing the adjusted value for the effect of males versus females. Adjusting meaning within different levels of age. Among young people or among old people, B1 is representing the adjusted effect of males versus females. And likewise, B2 is representing the effect of age controlling for men and controlling for women. It says control for sex. Look just among men and look at old men versus young men, and then look at just among women, compare old women versus young women. That's what the B2 term is representing, the conditional or the adjusted effect of age controlling for sex. So when you fit models like this, the coefficient of one term represents the effect of that risk factor on your outcome, controlling for what other factors are in the model. So if I fit this model, here's what my results are going to look like. My coefficient value is minus 1.98. Coefficient of male, the B1 term is 0.7137. That's different from what we had before. We had just the model male, just the risk factor male in it, because now I have another factor in the model, age 55. Its coefficient is 0.5171. I can take the coefficient of male and take the coefficient of age and turn them into odds ratios. The number 2.04 is talking about the effect of males versus females on your risk of getting coronary heart disease, controlling for age, saying men have twice the odds of getting disease than women do